So welcome everybody to the third session of this bank seminar. Today we have from Australia, where it is like 9 in the evening. So thanks a lot for the effort of being here. So we have Matt Langford from Australia National University, and he is going to tell us why breakfast can wait. So please.
Thanks, Esther, and thanks for the invitation. It's good to be part of the seminar, and it's not too late. Yeah, nine o'clock. Not so bad. Long days here in Australia at the moment. So hopefully we'll understand by the end of the talk why breakfast can wait. Maybe it's not that important, but we'll see. So the first, most basic object I want to talk about to sort of introduce the main ideas here is the heat equation, which hopefully we're all familiar with. So according to Fourier's laws, the heat equation, which is written here, time derivative equal to Laplacian, describes the temperature distribution, in this case of an infinite universe, R3, but also with an infinite history. So the time life of the universe is the real line as well in this case. Now, the heat equation is a diffusion process. So what it does is it tends to take heat energy from points where there's a lot of heat energy and move them towards regions where there's not a lot of heat energy, and thereby evens out the temperature distribution. So U here is the temperature distribution. And so what you might expect in this example is that, since this diffusion process, this mixing has gone on for an infinite length of time, then we might expect that the temperature of the universe is already constant. So this mixing has been going on forever. Temperature of the universe is constant, so we can't really have interesting heat phenomena in such a universe. But that's not wrong, right? That turns out to be wrong. So there are actually many non-trivial solutions to this equation, which are entire in space and time. So here's a couple. And maybe given these couple of solutions, you could probably even come up with your own in say one space dimension, for example. In fact, solutions with one space dimension well, in this case, this extends to 3 space dimensions because it has trivial derivatives in the other 2 directions. So our initial conjecture was wrong. We don't end up with constant temperature distributions, but nonetheless, as the following theorem shows, they are quite special. So if we impose a very mild condition, growth condition, so assume that at the present time, the temperature distribution grows grows at a slower rate than e to the x, e to the displacement, then in fact our conjecture becomes true again. The temperature is constant, and sorry, I should have also said we're assuming that we have a positive solution. So that's physically very reasonable. We expect temperatures to be positive. And yeah, in this case, we recover our theorem under this mild growth condition. And indeed, if we go back to these examples, we see that both hypotheses are necessary. So this example has sub-exponential growth, but is not positive for all time. And for this example, it's positive for all time, but has linearly exponential growth in space. So these 2 hypotheses are necessary conditions as well. And if you haven't seen this theorem before, it should be reminding you of an obvious elliptic counterpart, the Liouville theorem for harmonic maps. Okay, so for harmonic maps, you do ask that the solution be positive, but you don't impose any growth condition, and you still find that solutions are constant. For the heat equation, for caloric functions, you also require a sub-exponential growth condition. Or sublinearly exponential, if you will. Okay, and indeed, this kind of rigidity is a hallmark of ancient solutions to parabolic PDE. So by ancient, I just mean the solution has an infinite past, but for the heat equation, we don't lose any generality by a theorem of Witter. we can uniquely, for positive solutions, we can uniquely extend forwards in time. So this is really a property of ancient solutions, not necessarily. So the fact that the time interval stretches to the infinite future is not really relevant here, just the past. Okay, so a little primer on the heat equation. Beautiful theorem in this form due to Hirschman in 1952. Okay, so what I really want to talk about here are heat-like equations in geometry and in particular the mean curvature flow. So let me begin with the one-dimensional version of that, which is called the curve shortening flow. So in the curve shortening flow, you take a curve. For us, we'll just be considering planar curves. And you try to decrease its length as fast as possible, at least locally. And you get the curve shortening flow. And the Euler-Lagrange equation tells you that at each point, the velocity is equal to the curvature vector. So simple enough. And here's a little movie. So let's start off with some very tightly spiraled up curve. We have a point of very, very high curvature here at the tip of the spiral. And we have, so the spiral gets tighter as you move out, and we have low curvature near the middle, and also very low curvature around the edges of the spiral. So they almost look like very large circles. But we have a very large curvature here at the tip. And so what you'll see is that this tip will start moving very quickly, and it actually unwraps itself and then becomes sort of small, convex, and round and disappears at a point. Okay, so I just wanted to give that nice picture in your heads of what this evolution equation is doing. And in fact, maybe I'll even say some more. So what it's doing is it's taking regions of high curvature and making them sort of move inwards in order to decrease the curvature, while regions of relatively low curvature stay put. So in some sense, it's diffusing the curvature. But on the other hand, once it becomes convex, all of the curvature is in one direction and it shrinks down to a point very quickly. So the curvature then actually becomes very large. So you have sort of two processes going on here. The curvature is trying to become large, but it's also trying to even out. Appropriately viewed, this is it's in a very abstract sense, it can be written to exactly resemble the heat equation, but also if you view it in through a suitable gauge, you can represent it as a non-linear but nonetheless parabolic partial differential equation. But abstractly, it's exactly a heat equation for these curves, and we again expect to observe these kinds of rigidity properties for ancient solutions. And indeed we do. So in this case, so the curve shortening flow is the sort of the simplest case. So there's this theorem that says, you don't have to read anything on this slide, you can just look at the picture. It says that if you restrict attention at least to convex solutions, so solutions which at each time bound a convex region, then you only get these 6 examples. Well, the 3 on the left are kind of the same, but we're trying to distinguish the regions bounded here. So we sort of distinguish those. And then there are these 3 interesting solutions on the right. So there isn't a uniqueness theorem here, but we actually have classified all solutions. Our condition of convexity, this plays the role of the positivity condition in Appel's theorem or in Liouville's theorem. But by removing the growth rate, we don't really have a uniqueness result here. On the other hand, we get a complete classification of the solutions. So they're exactly these 3 interesting ones plus the less interesting ones on the left. Yeah, no growth rate required. The convexity condition, the key point here is convexity plays the role of the positivity condition. And indeed, it's just as in Appel's theorem.
Two questions, actually. So
yes.
First, what is the difference between a stationary line, a stationary strip, and a stationary hyperplane?
Not much if you're just looking at the curve itself, but here I'm just trying to distinguish the convex region bounded by the curve. So here I'm thinking of the flow really as a flow of convex regions, or boundaries of convex regions. And so I'm simply trying to distinguish the the regions bounded there, but yeah, otherwise not much. In some contexts, it's useful to make that distinction, but I guess today it's not that interesting. Was there another? Did you say you had a second question? Okay, and again, the condition is actually necessary as well. So there are, well, in fact, before I mention these examples, let's look at this Anganant oval example. In fact, let's look at all three examples. So we've got the shrinking circle, which is just a family of circles whose radii evolve according to an ODE. We have this solution called the Grim Reaper, which moves with the same shape. It just moves with constant bulk velocity to the right here. And then we have this sort of most interesting example at the top, which looks actually in an exact sense like two oppositely oriented Grim Reapers, at least when time is very, very large and negative, and then they eventually sort of come together and annihilate each other. Well, in a really interesting, fairly recent paper of Anganant and Yu, they showed that this phenomenon is actually much more general. You can basically glue together these Grim Reaper solutions as long as they're parallel. You can glue them together in basically any orientation. So you can glue them together in a kind of S shape, or you can have basically any orientation where you're allowed to scale them and you just line up the asymptotes. Then there basically exists an ancient solution with that configuration. None of those examples will be convex except for the one where they line up perfectly together, both asymptotes. But if you remove the convexity condition, you have all of these really interesting examples. And so things become much, much less rigid without the convexity condition. So that's another takeaway here. You really lose the rigidity. You have a very large configuration space, moduli space. Yeah. Okay. So how would you come up with these examples? The shrinking circle and the Grim Reaper, they're self-similar. One of them moves by scaling, which is a symmetry property of the equation. The Grim Reaper moves by translation, which is also a symmetry of the equation. And so in the curve case, that reduces the sort of seeking these examples to ODE, and the solutions you get in these two cases turn out to be ancient. It turns out that there is a kind of ansatz you can impose on the equation to reduce the Anganant oval to an ODE as well. And it's similar to what if you know much about minimal surfaces, there's an ansatz which you can apply to the 2D minimal surface equation in order to come up with Shirk's surface through an ODE process as well. It's a very similar ansatz in this case. Okay, so you can sort of come up with these very easy by suitable ansatz, ansätze, and solving an ODE. Showing that these are the only ones is, of course, much harder, but I'm not going to talk about that today. Okay, so that brings me to mean curvature flow, which is really what I want to be talking about. So this is a higher dimensional version of the curve shortening flow, or one higher dimensional version of the curve shortening flow. And so the equation says that you move a point on your hypersurface in the direction and magnitude of its mean curvature vector. Again, it's the gradient flow now of the area functional. So it is, in that sense, a direct generalization of the curve shortening flow. And also, in the same way that the curve shortening flow is an abstract or the abstract heat equation for curves, the mean curvature flow is very naturally can be written as a heat equation for submanifolds. And if you view it through your favorite gauge, you're likely to see a heat equation, a classical nonlinear heat type parabolic equation in that gauge as well. Okay. However, in this case, even in dimension 2, the ancient solutions are still a long way from being completely understood. Even in the convex case, without convexity, it's going to be a very, very hard problem. But even in the convex case, the landscape can be quite complicated. Okay, and I'll give some examples in the second half. Well, show how to construct two very interesting examples in the second half of part of the talk. But for the remainder of the first part, I just want to recall some useful analytic and geometric properties of the mean curvature flow. So the first property, which is a kind of maximum principle for this equation, says that if I start off with disjoint solutions, then they remain disjoint at later times as long as at least one of them is compact. There's no funny business at infinity or at boundaries. Okay, so these should be proper solutions as well, so they don't have boundaries. The contrapositive sometimes gets forgotten, but it's just as interesting. It says that if they do intersect, if these two solutions do intersect at some time, then they couldn't have intersected at earlier times. So often you'll use the avoidance principle in this form. So yeah, so two solutions can't form an intersection with each other. A new intersection. The next important property is the evolution of the enclosed area. So this is just the first variation of enclosed area for a family of hypersurfaces which bound regions. So you apply that formula for the mean curvature flow. It's very easy to derive. So the way the area changes should be the integral over the boundary of the speed. So a physicist would say this is obvious. A mathematician wouldn't have much trouble proving it. Okay, we're going to use that later. This is probably the most technical part of the first part of the talk. This is a very useful estimate. It's a kind of parabolic regularity estimate. It says that if I have a mean curvature flow where the surfaces are convex boundaries, then if I have some uniformly sized ball inside those enclosed regions, then I get a curvature estimate within the larger region in which these flows live. Okay, so our flows sort of live in a spatial region and a temporal region, and they enclose at the final time slice some uniformly sized ball. Then I get curvature estimates in a slightly smaller space-time region. Okay, but it's a kind of parabolic regularity property. In particular, we see that for a compact convex mean curvature flow, the flow will continue to exist until the area tends to zero. Okay, so by sort of parabolic regularity theory, if the curvature is bounded, well, in the convex case, if the mean curvature is bounded, then the second fundamental form is bounded, and you actually get estimates to all order by parabolic regularity. And this estimate tells you that in fact you continue to exist even until the area goes to zero. So the mean curvature cannot blow up until the entire surfaces, at least at the level of areas, disappeared. And in fact, a well-known theorem of Huysken says that the entire surface disappears at this final time, and it's asymptotically round as it does so. So just like that spiral curve unravels under curve shortening flow, any convex hypersurface will sort itself out and shrink to an asymptotically spherical point under the mean curvature flow. Two more properties I want to mention. So sort of a list of technical things we may or may not use later is this so-called differential Harnack inequality. So this is a magical thing, a magical property of the mean curvature flow, and extremely useful for studying ancient solutions. It says that if I have a convex mean curvature flow, then if I parameterize so that the normal direction at a point is fixed, so I just follow a point with a prescribed normal direction, then this quantity is non-decreasing. And in fact, we get strict inequality unless the entire solution actually evolves purely by translating with fixed bulk velocity. So it's called a differential Harnack inequality because when you integrate it under a non-time dependent parameterization, you get a classical Harnack inequality. We're not actually going to use that, but I thought I should mention it. And finally, so sort of to motivate what we're going to do here. So we saw in the classification of curve shortening flows, we had these two examples, the Grim Reaper and the Anganut Oval, which just live in a strip region. And then we had the shrinking circle, which sort of spans everything as you go backwards in time. There's a very beautiful theorem due to Shujia Wang. I probably should have given some credit for some of these things, which says that this is always the case. So if you have a convex mean curvature flow, sorry, a convex ancient mean curvature flow, then the enclosed regions either, as they grow backwards in time, they either sweep out all of space or exactly a slab region. So nothing else can happen. So these are the two cases of interest for convex ancient solutions. And the two different cases give rise to sort of different tools as well. So there's a whole big story, interesting story there that I won't go into today. But hopefully that'll motivate a little bit why we're going to look at this first case. So I'll stop there, end of part one. Yeah.
Okay, so after the nice introduction, some questions from the audience. So Nikita had one.
Yes, going back to the graphic with the different ancient solutions of curve shortening flow. Yes. What do you mean by collapsing?
Oh yeah, so excellent question. So for convex ancient solutions, I can say that it just means the slab dichotomy. It's either the enclosed regions sweep out a slab, a degenerate slab in the case of the line of multiplicity 2, or the enclosed regions sweep out all of space. Okay, so I've got an exceptional case here. Maybe I should say, yeah. But for the strictly convex case, say, that's equivalent to another definition of collapsing, which says that if I take a point in the enclosed region, sorry, if I take a point on the boundary and I look at the largest ball enclosed in the region which is tangent at that point, then its radius should be comparable to 1 over the curvature at that point. If that, it's a bit hard to say in words, but yeah, so for the shrinking circle, we call this the inscribed radius. So fix a point, look at the largest ball which is enclosed in tangent at that point. It's equal to the whole shrinking circle. And so the inscribed radius is exactly equal to 1 over the curvature, or 1 over n times the mean curvature. However, for the Grim Reaper and the Angadine oval, so for the Grim Reaper, it's a bit easy to see. If you move across to the right towards infinity, the inscribed radius is bounded, but the curvature goes to 0. So this is collapsing. So the inscribed radius is not comparable to 1 over the curvature. Similarly, for the Angadine oval, if you take an inscribed ball close, with center at the origin, then as time tends to minus infinity, the curvature above and below the origin tends to 0. However, the inscribed radius is bounded by pi, or however you normalize the solution. So it's not uniformly comparable to 1 over the curvature. But for convex ancient solutions, that turns out to be equivalent to this slab dichotomy as well, interestingly. There's a subtle relationship between the two. Maybe one further thing you could say is that maybe the first thing I should have said is that if you zoom out, then the enclosed regions, they collapse. So you sort of lose the interior. Whereas if you zoom out on the shrinking circle and sort of go backwards in time as you do so, then you still see a region of full interior. But for the Grim Reaper and the Angadine oval, if you zoom out, then the interior region actually degenerates. So yeah, that's a good way to think about collapse.
No?
So. Do you have anything else?
Yeah.
Yeah.
Let's go.
Mm-hmm.
Well, hi. So the second question that I have concerns the slab dichotomy. One of the assumptions that you have for the slab dichotomy is that the ancient solution sweeping out either a slab or the entire space is that it's convex. Let's say we remove convexity as an assumption. Is there a known example that doesn't sweep out a slab or all of space?
Excellent question. There is but it's not embedded. So there's these. So after the work of Anganan and Yu on these ancient trombones, when you join together these Grim Reapers to make these complicated examples, this was refined a little bit by John Manshun Ma, who showed how to construct an example which sweeps out a half plane. And it's given by joining these Grim Reapers together. You sort of have one Anganan oval, but then you sort of grow a little bubble on top, which is a smaller Anganan oval. And as time goes backwards, it sort of sprouts another little bubble on top. And so it would be like a figure eight configuration as they sit on top of each other. So it sort of grows backwards in time and then sprouts a new little Anganan oval looking thing on top. And then that gets wider as we go backwards in time, and it sprouts another one, and it keeps sprouting these little these extra little bubbles on top, and this does sweep out a half plane. But those are not embedded examples. So I think at the moment there's no known example of embedded ancient mean curvature flow which sweeps out anything else. There's also a theorem by I think Francesco Chini and Niels Martin Muller, which says that the convex holes satisfy. Wait, no, it's a little bit more subtle than that. So the convex hole of it might be an embedded ancient mean curvature flow has to either sweep out a slab region or all of space or a half space. And you have to include the half space case as well. In fact, even in this theorem, I have to include, the way I've stated it, I have to include a half space because of just the trivial example. But you can add to this theorem, I suppose you should add, if it's not a half space, then it sweeps out either a slab region or all of space.
I'm sorry, but I think if you remove convexity, you have all the minimal surfaces. So you get many counterexamples.
This is a good point, Oliver. Maybe you have to be very careful how you state the question, I guess. That's a good point. Yeah, the minimal surfaces, of course, don't move under the flow, so their enclosed regions are what they are. Yeah.
Great. Any more comments or questions? Well, if not, you can proceed with the second part and then more questions at the end.
Thanks, Esther. Okay, so let's move on to part two. So in higher dimensions, there is another example called the ancient pancake, which I'm going to describe. So basically what I'm going to do is just show you how to construct another example with certain properties. And the construction we go through gives an idea about how you might go about constructing these sorts of objects in general. So what we're going to do is construct a higher dimensional analog of the Anganan oval. So the idea goes as follows. So you take the Anganan oval, or you take some time slice of it, and you rotate that time slice. Well, you extend this curve to a hypersurface by rotating about the y-axis in this higher dimensional Euclidean space. So that gives us a nice convex surface. Of course, the resulting surfaces won't move by mean curvature flow. They've got this additional sort of rotational curvature, which would need to add to the velocity. So what you do, let's see, yeah, you don't just try and perturb this thing to get your solution. You fix a time t, call it s, and then you evolve this region that you got by rotating the time s slice. You evolve that by mean curvature flow. And then what you do, so we know that this has to contract to a point after some finite amount of time. We can just do a time shift that doesn't change the mean curvature flow. We just do a time shift so that the solution lives up until time 0, but started at some negative time. And then the idea is to show that as we choose this initial time slice earlier and earlier, then these mean curvature flows we've constructed live for longer and longer and actually tend to some limit, which is then an ancient solution. And this choice of initial condition, it's kind of has some useful properties that help us do it. So hopefully that's clear enough. So we want to construct, so Ungenant calls these old but not ancient solutions. So we try to construct a sequence of very old solutions and then take a limit to get our ancient solution. Okay. So there's a lot of, you can really get your hands dirty with this construction. So it's a good one to go through because you can really get a lot of, not exactly precise control, but you can control things fairly well. So the first thing we do is we just do our differential geometry homework, and we write out the second fundamental form. So it splits into this block diagonal form where you have one of the principal curvatures is the curvature of the profile curve, and we have these additional curvatures coming from the axial symmetry. Here theta is the angle the outer normal makes with the x-axis or the r-axis. So theta is 0 at the tip here, where the normal points in the direction of the x-axis, and then goes up to pi/2 at the sort of north pole. On the initial surface, you just do your differential geometry homework. You can show that that kappa is bigger than lambda, and it's non-increasing as you go from sort of tip to pole. You can also, you just differentiate this rotational curvature, and you get this nice identity. And so this is also non-increasing. And so when you add all of the principal curvatures together, you get a non-increasing mean curvature. This is a very useful property because it turns out to be preserved under the flow. The reason is that these objects, so the difference between kappa and lambda and the derivative of kappa and theta, these both satisfy along the profile curve linear parabolic equations. And then there's this classical theorem of Sturm, which says that the zero set of a solution to a linear parabolic equation in one space variable is, if the solution is non-constant, the zero set becomes finite at positive times, and the number of zeros is not increasing. And so you can sort of combine that with the symmetries of the curve to show that these properties in orange here are preserved under the flow, and they turn out to be very useful for controlling the geometry of the solution, as you might expect. So the first thing we do is we use the fact that kappa is bigger than lambda. We recall the evolution of area was the integral of the mean curvature. We integrate that up, use the fact that the area vanishes at the final time, and we get that the area is given by this exact formula. Along our profile curve, kappa integrates to 2 pi. Lambda is bigger than 0 and less than kappa, so we get these two estimates for the area. Very, very nice control over the enclosed area. Okay, that's the first thing we're going to use. We now use the fact that we know exactly what the area enclosed by the initial profile curve is, since it satisfies curve shortening flow with respect to S. So the area, or you can compute it, I suppose. So the initial area enclosed area is 2 pi S. And so we immediately get that the initial time is comparable to this parameter S. So we do see that these solutions exist for longer and longer times, tending to infinity or minus infinity, as this parameter S tends to infinity. Okay, so we've got sort of explicit control over how quickly the area decreases, and so we get explicit control over how long the flow lasts. So this means that if we can take this limit, then the limit will indeed be an ancient solution. But in order to take a limit, we need estimates for the curvature. If we can get estimates for the curvature which are uniform in this parameter S, then parabolic regularity theory kicks in. We get estimates in CK for every K, to simplify things a little bit. And then we can take our limit using the Artzela-Ascoli theorem. So our goal here, well, one goal, there's a couple more subtleties. One goal is to get estimates for the curvature. So how do we do that? We first estimate the minimum of the curvature. Okay, so what we do is we place a circle underneath the top half of our profile curve, which passes through the tips. And by the symmetry property and the monotonicity of the curvature along the curve, we find that this has to lie locally below our solution, and then you can compute the radius exactly, and you get an estimate for the curvature in terms of the short axis and the long axis, this h and L. So we get an estimate. We get our estimate for the mean curvature, only that we get our estimate at a point where the curvature is minimized rather than maximized. You then use the evolution of these axes, so the rate of change of displacements given by the speed, which is given by the curvature. So we're going to integrate these up, use the area formula, and apply the Harnack inequality to close the argument up. So what do we do? Okay, so our estimate for h at this minimum point looks like this orange estimate. So we're going to estimate the long axis. So since we have a convex region here, we can bound the area from above and below by L times h. That's relatively easy. So we can estimate using our area estimates, we can estimate the long axis from below by remaining time. We can then go back to our evolution equation for the small displacement, little h. We can now apply our estimate for L, and we get something very explicit. This now no longer depends on S, so we get a nice now lower bound for the minimum displacement. So this is excellent. We feed this back in to the area estimate to get an upper bound for L. Now that we've got a lower bound for H, so that we've got this nice upper bound for L as well. And now we integrate up the evolution equation for the largest displacement to get this first equality on the bottom line. And we apply the Harnack inequality to close things up. So we apply the Harnack inequality, which says that the square root of elapsed time times mean curvature is non-decreasing. And so that's how we get the inequality. And then we just integrate 1 over square root of remaining time is integrable. And so we get this estimate, which gives us an estimate at the point of largest curvature, an estimate for the curvature at the point of largest curvature. As long as t is not close to the final time. And so we've got everything we need now. So we've got an estimate for the curvature which doesn't depend on S. So we can take a limit to get our ancient solution. Since it's a limit of convex doubly symmetric objects, it's convex and doubly symmetric. Since we have an S-independent bound for the major axis, the limit's going to be compact. And since we have upper and lower estimates for the minor axis, we know that the limit sweeps out the slab of width pi. So just using these sort of 3 basic geometric tools and the differential Harnack inequality, we can estimate all the things we need in order to take a limit, and then we get this a solution that looks something like this. You can actually then go off and sort of refine these estimates and get very precise asymptotics for little l and h as well, but I won't go into that. In fact, you can get very precise asymptotics and use these asymptotics to show that this solution is unique within the ON symmetry class amongst solutions which sweep out slabs as well. So you can actually get precise enough asymptotics using these tools to get a uniqueness result as well. Okay, so I think there's sort of some nice geometry you can play with there to construct this guy. Oops, I've put that at the wrong place. And so for the final section of the talk, I want to show how you can construct a new solution by stacking 2 of these examples on top of each other and joining them by a neck. So that's the remainder of the talk. Okay, so we've got our ancient pancake solution. What we want to do is we want to take 2 of these solutions, and try and join them by an evolving neck. And so we try to play the same game we played before. We just join two very early time slices together with some neck. Then we evolve it and hope to see something that exists for a very long time, hope to get some control over it, and then take a limit as the initial configuration, the S slice tends to infinity. Okay, so we take these very early time S slices of 2 unit scale pancakes. We have sort of unit separation, and we join them by a neck of some radius mu. Okay. It'll become important at some point that our dimension is at least 3 here as well, the dimension of the surface. Okay, so we've sort of got some neck parameter we've used to join these two surfaces together. Now we evolve this guy by mean curvature flow to obtain some mean curvature flow. We've got some ambiguity here in how we normalize time, but I'll just leave that ambiguity there for the moment on where we fix our zero time. Okay, so we now observe that we want to exploit some Sturmian properties again, like we did before, but things are a little bit more complicated. So the profile curve in this case has 1 local minimum and 2 local maxima. And by the same kind of Sturmian property for linear parabolic equations in one space variable, these and the symmetry of the configuration, these properties are preserved. So we continue to have just 1 local minimum and 2 local maxima for the profile curve until, so there is something that can happen. So the number of critical points can decrease, but the only way it can decrease is if 3 of them come together to form 1. So the 3 critical points would have to merge together to form a local maximum, and the solution would have to become convex. The only other thing that can happen, as proved by Altshuler, Angenat, and Giga, is that the neck shrinks off to the axis. Okay, so 2 things can happen. Either the neck shrinks off and pinches at the axis, that's a singularity, or the neck grows and coalesces with the maxima. The whole thing then becomes convex and thereafter shrinks down to a point. Okay, so this is based on work of Altshuler, Angenat, and Giga. But we can now play with the neck parameter. So if we take a very, very large neck, then the initial configuration is going to be convex, and then the whole solution will remain convex and shrink to a point. But if we take a very, very small neck parameter, you can use a barrier argument to show that you have to have a neck pinch. So either way, we can define the height at y equals 0, the sort of neck radius parameter. So either way, no matter what happens, this will eventually decrease down to 1, say. And so we now normalize our time origin to say that this happens at time 0. Okay, so we've just time translated this solution so that at time 0, that's when the neck radius first reaches 1. Okay, so maybe the whole configuration became convex before that time, maybe it didn't. And now what we do is we play with this neck parameter mu and use the continuous dependence of our solutions on the initial condition to control the maximum at this time. So we can also use this parameter mu to say that at time 0 we have control over the local maxima. Okay, so you can think of this as a kind of eccentricity parameter now. Okay, so we just choose a number bigger than 1, say 10, and we just play with this parameter mu so that the ratio of the minimum to the maximum is equal to 10 at time 0. Okay, so this property is what's going to prevent our limit from becoming something dumb like maybe we just get a pancake back. Okay, so we're just going to fix this mu henceforth and ignore it. Okay, we want to know that our solutions exist for longer and longer. We want to get an ancient solution in the limit. Well, we can just use barriers. So our initial configuration contained very early time slices of the ancient pancake by the avoidance principle, the characterization of the existence time of these neck-like solutions, we know that they have to continue to exist until these pancakes disappear. So we know that they exist for arbitrarily long time as these initial pancakes become older and older. Okay, so again, if a limit exists, we'll get an ancient solution. It'll be a limit of doubly symmetric solution, so it'll inherit that property. It'll be compact because the time zero slice is compact, and non-convex because the time zero slice is non-convex, and confined to a slab because it'll be a limit of objects which are confined to a slab. And this is the properties of the solution that we want to inherit when we take the limit. Only problem is, again, we don't know how to take this limit. And worse than before, we don't know how to prove curvature estimates. So we don't know how to get curvature estimates to take a smooth limit. So we just take a weak limit. And namely, we take the limit in the measure theoretic sense of brachyflows. Okay, and that's we can do that because we only need very, very weak bounds, so Gaussian area bounds, and these are uniformly bounded by, say, 5. It's sort of a little bit more than 4 planes will bound the Gaussian areas. And now what we want to do is show that the limit that we get is smooth and satisfies all of these properties. Okay, that doesn't seem so trivial, obviously. But we're assisted here from the fact that this limit flow is happening for axially symmetric solutions for which the radial function is graphical. And so that actually is enough to tell us that we get some stronger properties for these brachyflows. We get that the time slices of the approximating solutions actually converge in the Hausdorff sense to the supports of the brachylimit flow. So this is much better than simply taking a limit as brachyflows, and it's crucial to controlling anything on the limit. So a very different idea here than before. So we just take the limit a priori and then show a posteriori that the limit satisfies what we want. And I'll only be able to very quickly go over how we go about that. And so the first thing we do, so we want to show that limit is smooth. We need to show a little bit more than that, but we'll first show that it's smooth. And we first rule out singularities forming on the axis. And this is motivated by something called the attracting axis theorem of Altschul, Angenan, and Giger. And the idea is just that once a neck gets close to the axis, it has to stay close, and then it can't then get large again. So once a neck gets small, it can't then get large again. And this is proved by using a catenoid barrier, and this is where we need n greater than or equal to 3. So the idea is that if the brachy limit has a singularity, well, that singular point has to be the limit of points on our smooth approximating flows. So that means that there are points on our smooth approximating flows which get very close to the axis. And then we show that it's impossible for these necks to then open back up again, which violates the fact that we've configured everything to have a uniform neck size at time 0. And the idea is just to use a catenoid as a barrier. However, we need n to be at least 3 for our catenoid to lie in a slab region here. And so what you do is you set up a catenoid with neck radius less than 1. And this will intersect the initial configuration exactly twice. By the Sturmian property, the number of intersections can't increase. So it will stay 2 as we move along the flow. But at some point, the necks have to pass because we know that the neck, so at our t star time, our neck is getting very close to the axis. So at some point, the necks have to pass. But at that time, the intersection number has to be just 1. So the 2 intersections become 1. And at later times, there are no intersections anymore. But because the catenoid has neck radius less than 1, well, at later times, the flow must then re-intersect because at time 0, it has neck radius equal to 1. So this violates the the maximum principle, basically. Okay, so we don't have any singularities forming at the axis. This is a key step in what follows. So we then employ a tangent flow analysis. So I won't be able to talk much about this, but you basically take tangent flows of this brachyflow to analyze the singular set, and exploiting the axial symmetry, the graphicality, and the absence of axial singularities, we can show that the smooth times are dense. So you sort of you rule out you look at what tangent flows can arise, and you rule things out. Anyway, there's a lot going into this argument, but that's very roughly how we do it. So the smooth times we get that the smooth times are dense. And now, to sort of finish the argument, we want to show that the supports of the limit flow are compact and connected at the smooth times. Well, it suffices to do this at a sequence of smooth times tending to minus infinity. Okay. And so in order to do that, so since the initial condition is connected, the only way we can lose connectedness or compactness is if the maxima on the approximators are pushed to infinity in the limit. So if we have a sequence of approximating flows for which the maxima are tending to infinity, this turns out to be the only way you can violate compactness and at the same time connectedness. But under this process, the resulting cusps will enclose finite area up to a given scale. And once you know that they enclose only a finite amount of area, you can show that area has to decrease to zero over a fixed amount of time. So the cusps have to, if they do form, they have to vanish again very quickly. And so if you do have a smooth time at which these cusps at infinity are forming, they disappear again very quickly. So at a later smooth time, you know that they're not there anymore. Is very roughly the idea. And so you really get that the flow's back in a uniformly bounded region a short time later. So we then have a sequence of times at which the flow is smooth, compact, and connected. But once you have a smooth, compact, connected, axially symmetric mean curvature flow, the only way that can then become singular is for either the neck to pinch off at the axis, or for it to be convex and then the whole thing to collapse to the axis. But because the final time slice still has its neck, that can't happen. So that completes the argument in a very, very quick sketch. So I should probably stop there, because I think I think I'm over time almost.
Okay, so thanks for the nice talk.
Don't feel the need to ask these questions.
Time for
I'm not leaving
questions.
that.
So it's me again. I have a question maybe. The profile curve of these two stacked pancakes, it's not going to be an ancient solution of curve shortening flow, right?
No, definitely not. It has to move. So the mean curvature gives it a little bit of additional speed. So maybe that's outward or inward depending on the point you're on, but because the rotational component to the curvature points outwards at the neck and inwards at the tips, and that adds to the speed of evolution of the profile curve.
Anything else? Well, actually, I have one. Do you know, even for the curve shortening flow, what is known about classification of ancient solutions if you are not in a plane, say in hyperbolic plane or?
Yeah, I think it's very much open, but I think it's very much open. In the hyperbolic plane, there are definitely a lot of interesting questions you could pose. You might look at horospherically convex curves or things like that. But I think on, say, compact surfaces, maybe this is kind of known by a combination of known results, but you should only see solutions out of unstable geodesics corresponding to the Morse index of those geodesics. For non-compact surfaces with, say, positive curvature, I think that's a really interesting place to try and classify the convex ancient solutions, because you should have analogs of sort of things that come in from infinity, like the shrinking circle. I think under positive curvature, you probably won't have things like the Unguent oval. So there's definitely a lot of interesting questions there. I don't know that anything's very much has been stated explicitly there.
Okay, so thanks. And well, can you use like the 2 or 3 minutes to comment the open questions you had in the last slide?
Sure. Oh, let's see. Okay, so a couple of things kind of stand out with this construction. So the separation between these two pancakes was arbitrary. We just chose it to be one, these initial pancakes. And also the eccentricity parameter at the final time, we chose the max ratio of maximum to minimum to be equal to 10. So these are totally arbitrarily chosen. But if you vary these parameters, the question is, do you get distinct solutions or not? We don't know. I think you definitely should get a family of solutions here, not just the one. And in fact, we only stacked 2 pancakes on top of each other. We're originally hoping to do more, but we really exploited in various places here the fact that both of the maxima, the local maxima of the 2 pancakes, agree. If you stacked a third pancake, they would interact with each other in an asymmetric way. And the top and bottom pancakes, if it was symmetric, would look the same, but the middle one might evolve with a different maximum. So as you start to try and stack more on top of each other, things get more complicated. Maybe modification of what we do here can deal with that, maybe not. Certainly not exactly the same. And I think an interesting example to try and construct here would be a sort of half infinite stack. You stack infinite many on top of each other to construct a kind of embedded version of this example of Ma, which sweeps out a half space. And so maybe on what Oliver pointed out correctly before, maybe I was crossing my wires with coming up with an example which sweeps out a half space. So I'm not sure if that's known or not. So this gives you a candidate. So if you can work out how to stack more than 2 pancakes together, you can probably stack infinitely many. And so I think that would give a very interesting example. Also, I mean, why do you have to stack them symmetrically? Maybe you can put them off center. I mean, they're converging to pairs of planes. I'm not sure that they necessarily have to be stacked on the same axis. There might be very general construction here, as in the curve shortening flow case, except we get embedded examples here. But yeah, that's basically. Oh, and also in the n=2 case, so we needed the fact that our catenoid lies in a slab. Things are definitely more interesting and more subtle in dimension 2. I mean, if you could construct such an example in dimension 2, at time minus infinity, it would have to explode out of a scaled down catenoid. It would have to evolve out of a catenoid, but because it would have to lie in a slab, that catenoid would have to be scaled down to 0. So the solution would actually evolve out of a hyperplane of multiplicity 2 in the middle, and then 2 planes above and below. So the 2-dimensional example would be more interesting as well, but we can't construct that. So that's kind of the further directions here.
Okay, so thanks. Interesting agenda. Any more comments? Well, if not, let's thank Matt again.
Thanks for having